Welcome everyone in Taiwan. Morning, good morning, and in America, of course, evening. And um, we're very happy today. We have a young scientist, Professor Sonia Tikoo from Stanford, to give us a talk on the. It should be like the time evolution of the lunar dynamo. Is that the title, right? I think it's the title.
Yeah, Lunar Magnetism.
And Sonia was educated at MIT, and before MIT, he did her undergrad at Caltech, and then after MIT, she was specialized in the lunar magnetism, and then after MIT and postdoc, and she went to Rutgers as an assistant professor for 3 years, and now she's at Stanford as a professor for geophysics. And her specialty, as you will hear, is on paramagnetism, and especially the rock magnetism. And from that, today she will talk about the evolution and maybe the dynamical lifetime of the lunar dynamos, which is a very interesting topic because it also have to do with the life history of the moon. Now, let's welcome Professor Tikoo, please, Sonia.
Great. Thank you so much for the invitation and the warm welcome. And I'm very excited to be talking with you all about lunar magnetism today. Before I talk about the moon, I'm going to give a little bit of a primer on planetary dynamos. Planetary dynamo magnetic fields are generated by advection of conductive fluid inside a planetary body. Typically, in order to have a sufficiently conductive fluid, that fluid needs to occur in the liquid metallic core within differentiated planetary bodies. So if you can show using paleomagnetism or spacecraft observations that a planet currently generates or once generated a dynamo field, it pretty much tells you that that planet has undergone segregation into a metallic core and a silicate mantle early on in its history. And the second thing that tells you is that there is some mechanism operating within the body to sustain advection of the fluid metallic core. And that mechanism can be one of several things. You could have the canonical generation mechanism, which is simply thermal convection. So if you have a long-lived dynamo, that tells you something about the thermal evolution of the planetary interior and the cooling of the core. After a core cools down enough that it can start to crystallize, you can have additional energy sources to help power the dynamo, such as latent heat release or chemical buoyancy that are associated with inner core growth. And finally, in the context of the lunar dynamo, we may also talk about some more exotic mechanisms that can sustain a magnetic field, such as mechanical stirring of the core by external perturbations. And so if we take a walk around our solar system, what we find is that there is some history of magnetic fields operating on most of the kind of rocky bodies in our inner solar system in particular. Right now on Earth, you're sitting in a nice around 50 microtesla magnetic field. If you go smaller in planetary size and look at Mars's crustal magnetic record indicates that that planet once generated a dynamo field that went extinct somewhere around 4 billion years ago, although there is some recent evidence that it may have transiently turned back on again for a little while after that before ceasing permanently. If you look at Jupiter's moon Ganymede currently generates a dynamo with about a 700 nanotesla magnetic field. Mercury, our innermost planet, generates a dynamo field with an intensity of about 200 nanoteslas at the surface. And then finally, if you go down very small in size to bodies that are a few hundreds of kilometers in diameter, there have been an increasing number of paleomagnetic studies of meteorites that indicate that asteroids and early planetesimals generated short-lived dynamo fields within the first tens of millions of years of the solar system. And so the moon is an interesting target to understand dynamo evolution because it falls into a size range that's intermediate between bodies with longer-lived fields like planets and bodies with shorter-lived fields like asteroids. So from that perspective, it's a great natural laboratory to study magnetic processes. And so when it comes to the moon, the big questions that we are trying to address are, there's no current dynamo field operating on the moon. We have known this since very early on, since the Russians first launched probes to orbit the moon and measure its crustal magnetism. But we were interested in learning, did the moon generate a core dynamo in the past? If it did, how strong was that field? How was it powered, and how long did it last? And so today I'm going to first cover sort of a historical development of the field of lunar magnetism. I'm going to follow that up by talking about possible dynamo mechanisms. Then I'll cover the paleomagnetic methods that we use to study lunar rocks and some of the more recent results we have gotten in lunar paleomagnetism. And then I'm going to close by talking about the implications of the lunar magnetic record. And I'm also going to tie in what we've learned from some spacecraft observations of remnant crustal magnetism on the moon. So starting with the historical development, our first measurements of magnetic fields at the lunar surface were done by magnetometers on the Apollo missions. And so depending on which Apollo mission was measuring the fields, they found crustal fields of 3 to 300 nanotesla at the various Apollo landing sites. These numbers are way weaker than the Earth's magnetic field, but they are also non-zero. And they indicated that there was probably some kind of magnetic history on the moon. Then our understanding of lunar magnetism advanced because the astronauts were able to collect samples on the lunar surface and bring them back to Earth, where they were studied in paleomagnetism laboratories. And so during the Apollo era, there were a suite of paleomagnetic measurements that were done on dozens of Apollo samples. And what I'm showing on this plot here, on the x-axis is the time before present, and the y-axis is the paleo intensity value obtained for each Apollo sample, and each different sample is given by a different black dot on this plot. And these paleo intensity values assume that all of these rocks are basically the equivalent of igneous rocks in that they formed at high temperature and cooled through their Curie temperature in the presence of a magnetic field and recorded a thermoremnant magnetization. And so what we see from this early Apollo era timeline is that early on in lunar history, around 4 to 3.5 billion years ago, there's a lot of scatter, but there seem to be numerous data points of very high field intensities comparable to the Earth's magnetic field, or perhaps even higher. After about 3.5 billion years ago, there seems to be some kind of decline, but these values are also non-zero and often extend into the tens of microtesla range. And having some of these high intensity values relatively recently was surprising, given that the moon doesn't have a field today. So how long can we expect a small body like the moon to actually generate a field? So there were some questions that were left over at the end of the Apollo era. One, we didn't have much data before 4 billion years ago because there just weren't that many rocks collected from that age range that were suitable for paleomag studies. So we didn't know what the state of the earliest dynamo was. Another issue was that thermal evolution models of the moon, given its small size and its small core and the cooling of that body, would theoretically predict that a lunar magnetic field powered by convection should not be stronger than even 1 microtesla or 20 microtesla at the absolute maximum. So the fact that we had intensities that were greater than that was very mysterious. And then finally, these same thermal evolution models predict that you should not have a lunar core convection and heat loss from the core after about 4 billion years ago initially. So the fact that we had high paleo intensities after that was also mysterious. So this really prompted us to revisit Apollo samples and really dive into their magnetism again. Another thing that compounded the mystery of lunar magnetism was the moon has these crustal magnetic anomalies in the lunar crust. So you can see the areas of weak magnetization are sort of in the blues and purples, and the strongest crustal fields are found in the areas that are red. And what we see is that some of the strongest anomalies, like over here and over here, are located at the antipodes of the large impact basins on the moon. So the impact basins are in white and their antipodes are in black. And so this antipodal relationship between crustal magnetic anomalies and impact locations led to this question of whether lunar magnetism may not be related to a dynamo at all. Could it be the result of an impact-related process? And so more recently, there have actually been some models that investigate this possibility of impact generated or impact amplified magnetic fields. And what they have found is by simulating impacts occurring on one side of the moon and seeing how the plasma cloud wraps around the moon and converges at the antipode, they wanted to see how much any ambient solar system magnetic field could be compressed at the antipode and how much it could be amplified to see if you could get high field intensities. And it turns out from this more recent modeling that this process doesn't really produce very strong fields at the antipode. Generally, the fields that are produced are less than 100 nanotesla, which is very weak and certainly much weaker than the paleo intensities that we've retrieved from Apollo samples. And so what this is telling us is that there very likely had to be a dynamo operating on the moon to produce the magnetization that we see in rocks and in crustal anomalies. So nevertheless, that was a very recent study. Unresolved at the end of the Apollo era were these questions. Were there actually substantial 10 to 100 microtesla fields on the ancient moon, or could some of those data points be contamination from like terrestrial sources somehow? If these are real, what actually caused the magnetic fields? Were they a core dynamo or were they impact generated fields? We're leaning now towards the core dynamo hypothesis. And then if there was a dynamo, how was the dynamo generated and when did the dynamo decline and ultimately cease? All right, so next I'm going to talk about the types of mechanisms that could have powered a dynamo on the moon. There have been a suite of geophysical measurements, including seismology, that indicate that the moon does have a core that's probably less than 500 or 400 kilometers in radius. This is an example of seismic measurements that indicate that there are changes in wave speed that occur at certain layers in the lunar interior, and these layers have been interpreted to reflect a partial melt layer that overlies a fluid outer core and a solid inner core. So now that we know that the moon probably has a core, that's a good place to start generating a dynamo. So I'm going to talk about 4 possible core dynamo power sources, broadly speaking, that could have contributed to the lunar magnetic field. 2 of these are convective. So the first one is similarly thermal convection, where the lunar core is cooling and you have convection of the core, and that organized motion of metal in the core is generating the field. And then once you have an inner core that starts to crystallize, you can have a longer-lived dynamo sustained by thermochemical convection. Then there are 2 other dynamo mechanisms, which I would say are mechanical in nature. The first is this hypothesis that large basin-forming impacts on the moon could have actually perturbed the moon in such a way to cause librations. So the moon's like wobbling a little bit back and forth after each impact, and that can incur turbulence in the core, and it can generate transient magnetic fields that last for thousands of years after each individual impact. And that idea was published by Labars et al. In 2011. And then there was this other mechanism that has been considered for the moon, is this idea of precession, where you can have turbulence in the core generated by differential rotation, either between the fluid outer core and the solid mantle that overlies it, or differential rotation between the solid inner core and the fluid outer core. And so regardless of what boundary you're talking about, you can have precession that contributes to the generation of a fairly intense dynamo field according to those models. One thing that I want to add, which is a newer result, is that there's also been some speculation about whether the moon could have had a basal magma ocean dynamo in that partial melt layer that overlies the core. But we don't really know if those silicate fluids are conductive enough for sure to generate a dynamo, but that's on the table too. But regardless, this is the suite of possibilities that we're dealing with. And each of these mechanisms has sort of a different predicted lifetime. Thermal convection dynamos, pure thermal convection, are not thought to last very long. They could last till about 4 billion years ago, or perhaps a little bit longer, up to 3.5 billion years or so, if you can have like water in the lunar mantle, which sort of changes the convection behavior in the lunar interior. Then you can have these transient impact-generated dynamos, which persist as long as there are basin-forming impacts on the moon. And we think those ceased about 3.7 billion years ago. We're not quite sure how long a precession dynamo could persist. The precession, particularly between the lunar mantle and the lunar core, is driven by the distance that the moon is away from the Earth. It's controlled by sort of the Earth-moon gravitational influence. And so depending on how quickly the moon was receding away from the Earth in the past, the lifetime of that type of dynamo could be anywhere between 2.8 billion years ago to even less than 2 billion years ago, and we don't really know. And then finally, there have been a few papers written about thermochemical convection sustaining a long-lived weak dynamo, and those could last till about 500 million years ago. So that's what's being discussed on the table. But we need to do paleomagnetism to get an accurate paleointensity history of the lunar field and actually use that paleointensity history to try to discriminate between different field generation mechanisms. And so whenever we do paleomagnetic studies of rocks, we're looking for a few things to try to say that that rock actually contains a dynamo record. The first thing that we're looking for is if we study multiple subsamples of a rock, all those subsamples have to have unidirectional magnetizations with respect to each other. The whole rock must be uniformly magnetized. If there was no dynamo field at the time that a rock formed, all the individual magnetic grains in the rock would be magnetized in different directions, and this would add up to a resultant zero field magnetization. So if we see a unidirectional magnetization, that's some good evidence that that there may have been a field at a time that a rock formed. The second thing that we're looking at is we want the magnetization vector to become origin trending when we do demagnetization experiments. What does that mean? All right, whenever you have a rock in nature, the rock contains a bunch of different magnetic grains inside it. And some of these grains, which I show in red, are beefy magnetic grains that are resistant to being reset by secondary effects or secondary magnetic contamination. And then there are some grains that I show in blue here that are kind of weak. They have what's called low coercivity, and they are easily reset. And sometimes these weak grains can pick up remagnetizations from long-term exposure to the Earth's magnetic field, coming in contact with tools that happen to be magnetic during sample processing, that kind of thing. And so whenever we take a moon rock in the lab, we actually take its natural remnant magnetization, which is the magnetic vector in the sample before we do anything to it. That's the natural state, and we demagnetize it stepwise, either using heating to increasing temperatures up to the Curie temperature, or we use alternating magnetic fields to randomize magnetization. And so if I use alternating magnetic fields in this cartoon, I'm demagnetizing my rock to some field strength, let's say 10 millitesla, and at that field strength, I have randomized all the weak overprint contamination grains in my sample. And then I'm going to keep demagnetizing this rock until I obtain an origin trending vector. And this is the primary magnetization in the sample corresponding to the time that it formed on the moon, if it exists. Then if we can obtain that origin trending magnetization, we can try to figure out what the paleointensity of the field was that produced that magnetization. And the basis for paleointensity experiments is that if you have an igneous rock that started out hot, and if there was a field present, magnetization within grains will be preferentially aligned in that field direction, and that'll result in a pretty much semi-permanent magnetization that is recorded in the rock. If a field is weaker than some ideal saturating state, this process is less efficient and you have a weaker total net magnetization, although it is still preferentially aligned in the field direction. And again, if there's no field around, there's nothing to bias magnetization directions and you have a net zero magnetization. But the takeaway here is that the magnetization in a rock is oriented towards the direction of the field, and the strength of that magnetization is directly proportional to the strength of the magnetic field. All right, so now I'm going to talk about some of the studies we have been doing in lunar paleomagnetism recently and what we have learned from kind of remeasuring some samples that were studied during the Apollo era. The first rock I'm going to talk about is a 3.7 billion year old Mare basalt from Apollo 11. It's called 10020. We studied this sample because it had no petrographic evidence of shock. Shock can reset magnetization, so we wanted to avoid that. It has a slow cooling time. It took probably days to weeks to cool down, and that is much longer than the expected 1 day or so maximum duration of impact-generated magnetic fields. So we wanted to be able to exclude that as an option for source of magnetization. And then finally, we had done argon-argon thermal chronology on this sample, which is temperature sensitive, and those results told us that this rock had only experienced day-night cycling to about 110, 120 degrees C since the rock formed, and that is much less than the Curie temperature of iron, which is 780 degrees C. So this rock cannot be thermally remagnetized on the moon. So whenever we studied this sample, we did a demagnetization experiment. And what I'm showing you on this plot is the magnetization vector, which is three-dimensional, projected onto a two-dimensional plane. So all the plots that are in black, all the points that are in black are showing the projection of the vector into the northeast plane, and the white dots are showing from the vertical east plane. And so what we see, if you just choose one color to look at and not the other, let me look at, let's say, the white dots, is that we removed some overprint magnetization shown in blue, and we obtained an origin trending primary magnetization in red. So we met that criterion for this rock. We found an original magnetization. We measured several different subsamples of this rock, and their magnetization directions when plotted on an equal area stereo net were the same as each other. So they were unidirectionally magnetized. And we did a paleo intensity experiment on this rock and found that it recorded somewhere around a 70 microtesla magnetic field, similar to the Earth's field intensity today. And so kind of in the, 2012 to 2014 era, we kind of had measured several Apollo samples from this period in time between about 3.8 and 3.5 billion years ago, and this one sample at 4.25 billion years ago. And what we found was there is evidence for a lunar field that is several tens of microtesla in intensity, potentially up to 100 microtesla in intensity. And then that field appears to be robust. The question is, was it always that high? We're actually still working on that. There were some lower paleo intensity values that were obtained during the Apollo era, and we actually need to go back and remeasure those weak field samples and see how much variation there was. But regardless, there is evidence for a strong field early in lunar history. But the question is, what happened after that? What happened after about 3.5, 3.6 billion years ago? Well, I initially started to come into this. I need to update some of the dates on these because this paper actually came out. Whenever we demagnetize some of these younger Mare basalts, we often get really messy demagnetization patterns. This X shape is simply formed by like a rock that has one magnetic grain that's dominating the entire signal, and the magnetization in that one grain is flipping back and forth along one axis. So some of these rocks don't have great magnetic recording properties. Here's the demagnetization of another rock. We removed some overprint component, but then it didn't have an origin trending vector. It sort of decayed into noise at higher fields. And so the question is, what's causing this type of behavior? Does that mean that there was no lunar magnetic field, or does it mean that there's something wrong with our rock magnetic recording properties? And what we found early on is that it turns out that a lot of lunar basalts in particular are really poor magnetic recorders. They have very large grains of iron nickel, and in paleomag, the larger your grains are, they tend to be worse and worse magnetic recorders. And so what we found is that if you imparted the rock with a magnetization in a weak field, its demagnetization would be very noisy. But if you used a stronger field and demagnetize that, you would actually be able to retrieve a linear magnetization vector down to the origin. So what this tells us is that there may have been a lunar field, but you can't retrieve records from it if it was less than a certain threshold value. So then what we did was we tried to determine what is that threshold value for different samples. And what we found is that some rocks are better recorders than others, but generally by about 3.2, 3.3 billion years ago, the lunar field was likely less than 7 microtesla or to 10 microtesla most of the time. So that was one of the takeaways that we got, is that there appears to be a significant decline in the dynamo field intensity. But we couldn't figure out if the dynamo was actually off or not. And so that was a question that persisted. And so we wanted to reconcile this by finding a rock that was a really good magnetic recorder, not something kind of bad like these Mare basalts. And so what we found was there was this Apollo 15 regolith breccia. This is basically, the lunar regolith is basically all these broken up rocks at the surface due to impacts. And sometimes because of impacts hitting those rocks, it can melt a localized pocket of regolith materials and clasts and weld it back together into a new rock. So you have a bunch of clasts and you have impact melt glass between the clasts. And so what was cool about this glass was it had really fine-grained good magnetic recorders. And so we thought maybe this would be a good rock to study. So this rock is young. Our thermochronology experiments suggest that it's between 1 and 2.5 billion years old. More recent dating has shown that it's closer to 1.3 billion years old. That's kind of the age that we're going with now. And it cooled very rapidly, as evidenced by the presence of so much glass in the interior. So we think it cooled about over a time scale of hours after it was initially lithified. And again, this rock has great magnetic recording properties. Here is on the top half is a basalt clast in the rock, and you can see this big clunky iron nickel grain. But then in the amorphous glass portion that's adjacent to it, you see that there's very, very fine iron nickel grains. And those are the really good magnetic recorders. What was also nice about this rock was that the glass portion of the rock did not have any microfractures in the glass, indicating that that rock, after it lithified, had not been shocked again. So we could sort of rule out shock resetting of magnetization there too. And what we found when we demagnetized that sample, and we actually demagnetized it both using alternating fields and in a thermal oven in a controlled atmosphere, we had to reproduce the oxygen fugacity of the moon, which is a reducing environment. And we studied about 12 subsamples from the glass matrix portion of that breccia and found that, yeah, they had some overprint magnetizations. But once we got to the origin trending component, or the green vector here, all of the samples had a unidirectional, more or less, origin trending vector. So there was evidence for a young lunar dynamo about 1.3-ish billion years ago. And we were actually able to do a thermal, what's called the Tellier-Tellier paleointensity determination for this rock. This is the method that's typically used on Earth rocks, but we weren't able to do it on lunar rocks prior to the controlled atmosphere oven. And we found evidence that this rock recorded a 5 microtesla magnetic field on the moon 1.3 billion years ago. So this is a more updated version of modern lunar paleointensity studies. We have early evidence for a strong dynamo, again, early in lunar history. There's evidence that the dynamo field declined in intensity by about 3.2 billion years ago. We have this one sample that shows a dynamo record around 1.3 billion years ago. And more recently than my work, there was a paper out of MIT that measured 2 younger regolith breccias that were similar in lithology to this rock, but they were not magnetized. And they could put upper limits of about less than 100 nanotesla on the field at the time those rocks formed. So they say that the lunar dynamo probably ceased by 1 billion years ago. So we have this record that we are working with now in terms of the moon's paleointensity history. Strong fields, they get weaker, it's still alive, but then it dies. So now we have to make sense of what does this paleointensity record actually mean for lunar evolution. So this pattern tells us, I think, that the lunar dynamo may have been powered by at least 2 or 3 different mechanisms that operated perhaps at different times or perhaps simultaneously. Early on in lunar history, whenever the lunar core was able to cool efficiently, sure, you could certainly have a dynamo powered by thermal convection, but it's been really hard to get a convective dynamo to have sustained strong fields all the way through about 3.5 billion years ago. So if you're going to sustain a very high field for that amount of time, you probably need to have a different type of power source, such as the precession dynamo. And so that is a strong contender for the high field period of the moon. The alternative possibility is maybe those high paleointensity values are kind of biased and they're only representing transient spikes in the lunar field intensity. And if it's the latter case, then maybe we can fall back on the convective dynamo mechanisms, and maybe just some transient episodes where due to kind of mantle convection patterns or something, that you could have little intervals of cooling at the core mantle boundary that's more intense, and you could have, you know, more rapid heat loss for transient spikes. So that's something that we're discussing for that period of lunar history. And then as you get to the younger part of the lunar paleointensity record, it really seems like you can only invoke core crystallization to sustain a weak, very long-lived dynamo after about 3.5 billion years ago. So that's our current understanding of the moon's paleointensity evolution from the modern studies. And we're definitely still working on this. I'm definitely studying rocks from the high field epoch that didn't have strong paleointensities, and I'm trying to figure out what might have been going on there. Are those rocks not magnetized? Were they demagnetized by shock? Are those really low paleointensity values? That's kind of ongoing research. But this is what we've got right now. So what I'm going to do here in the last 15 minutes or so is I'm going to transition and start to talk a bit about what we have learned about lunar magnetism from spacecraft observations and orbiters that are really looking at the crustal magnetism in the moon. So we've had several spacecraft now that have taken magnetic measurements of the moon at a global scale. The first one is Lunar Prospector, which had a magnetometer on it. And then there were also additional magnetic measurements made by the Kaguya orbiter that was sent by Japan. And so basically, with a combination of the Lunar Prospector data and the Kaguya data, there have been a series of magnetic maps that have been produced for lunar crustal magnetism. And so I think on the left here, we're looking at the total field anomaly of the moon. And what we're seeing is that there are some areas in the lunar crust that have very intense magnetic anomalies. And I showed you on that earlier slide that some of these anomalies happen to be co-located with the antipodes of basins. But there are other possibilities for why they exist. And I'll get into some of that a bit later in this talk. But one of the advantages to studying lunar crustal magnetism over paleomagnetism right now is that the Apollo samples that were brought back were not oriented. They were regolith float. They were just rocks that were lying on the surface of the moon for the most part. I'm going to say for the most part because there are some rocks that may be orientable. And there have been some preliminary works done on those. But for the most part, we don't have that information. So we can't learn anything about the geometry of the moon's magnetic field from paleomagnetism quite yet. So what people are able to do is they are able to find isolated magnetic anomalies on the moon and use magnetic inversion techniques, particularly equivalent source dipole methods like Parker's method. And they invert and try to obtain the direction of magnetization responsible for each of the magnetic anomalies that are present on the moon. And one thing that's been a fascinating outcome of these inversions is that we don't get a coherent paleopole direction for the moon if you assume that the moon had some kind of dipolar field structure. So on the right is a plot from Oliveira and Wazorek 2017 that shows paleopole positions obtained from the moon. And what you see is that they are sort of all over the place, kind of strangely along the north, south, east, west Great Circle, which is kind of fun. But we don't have coherent results from these paleopole inversions. So this is again motivating us that maybe we need to go back to the moon and get oriented samples to actually do lunar paleomag again and try to get a correct field geometry for the moon. If it turns out that we do not have an axial dipole from paleomagnetic measurements, that could be evidence that maybe if the moon had a dipolar field, that it was not axial, or if it had, or maybe it didn't have a dipolar field at all. Maybe it had a field that was multipolar. And so there's a lot of work to be done in the future, kind of constraining the lunar field geometry. So The next thing I want to talk about is lunar swirls. And you may or may not have heard of lunar swirls, but again, here is a map of a lunar crustal magnetism superposed on the lunar terrain. And what we see is that there are several regions that have very strong crustal magnetic anomalies, but a lot of these really strong magnetic areas have features on them called lunar swirls. And I'm going to tell you what a lunar swirl is, but their locations are shown in pink here. I'm going to tell you about this lunar swirl right here. That area is a region called Reiner Gamma. And Reiner Gamma is, again, a swirl. What is a swirl? A swirl is an area that contains alternating light and dark surfaces on the moon. It is a brightness or albedo anomaly. There is absolutely no correlation with local geology or local topography. They almost appear like they have been painted on the lunar surface. So their origin is a real mystery. And the only thing we really know about them conclusively is that they exist in areas where there's very strong remnant crustal magnetization on the moon. And they have very short length scales. The light-dark transition occurs over a distance of a few kilometers. And so the running hypothesis is that the morphology of the lunar swirl and how it appears on the surface may be controlled by the geometry of the magnetic field in that region. So the idea is that there's probably some very strongly magnetized magnetic source body underneath the surface, and then the field from that body is somehow affecting the formation of the swirl. And there's sort of two main hypotheses for how this could happen. The first one relates to space weathering. And so the idea there is that you have a magnetic source body and it has a field that's being emanated from that source. And in areas where the magnetic field is vertical, the charged particles from the solar wind can actually follow the field lines and interact with the lunar surface and cause darkening and space weathering. And that's where you get the dark lanes from. And then in areas where the fields are more horizontal, those areas are protected from these charged particle interactions and space weathering. And so they retain their original sort of primitive bright color. So basically it's differential space weathering that is one of the hypotheses for forming swirls. The other one is that maybe somehow these magnetic fields are causing some kind of electromagnetic sorting of regolith fine material. So maybe areas that have more nanophase iron that are darker spectroscopically or visually will kind of migrate to the dark lanes of the swirl, and then the rest of the material is bright. So there's a few different hypotheses floating around, but there's definitely a strong interest in looking at the space weathering component of lunar swirls and how much shielding you might get at a lunar swirl from the solar wind. And so we wanted to think about what could be the magnetic source body that underlies a lunar swirl. And I wrote a paper with my co-author, Doug Hemingway, where we argued that based on the morphology of lunar swirls, particularly given that the light to dark transition length scale is so small, on the order of single-digit kilometers, that lunar source bodies, they need to be narrow and they need to be shallow in order to produce such sharp field geometry transitions. And so we looked at a bunch of different geological features. We considered things like dikes and lava tubes, Mare basalt flows, basin impact melt sheets, impact ejecta and impact breccias, and also remagnetization by comet impacts, which is a hypothesis that was advanced by Peter Schultz. So what we found was when we considered just the morphology, dikes and lava tubes can create narrow features that are shallow. The question about those is that most Mare basalts brought back from the Apollo missions are not nearly magnetic enough to produce the magnetization required to form a lunar swirl. You need magnetizations that are greater than about 0.5 amp per meter, when most Mare basalts are less than 0.1 or even 0.01 amp per meter. So they are not typically magnetic enough, but it's possible that there are heterogeneities in metal content in lunar igneous rocks that we don't know about because Apollo just didn't sample those rocks. Then Mare basalt flows are unlikely because even though they're shallow, they are not narrow. Basin impact melt sheets can also be shallow but are not narrow. Impact ejecta is certainly a strong contender. You could have asymmetric ejecta deposits that create rays or land in clumps that can have different morphologies. And because of the presence of impactor-derived metal, like say you have an iron meteorite, or say you have a chondritic meteorite, which still contains a lot of metal in its body, having ejecta from that type of an impactor being dispersed would have areas on the lunar surface that have stronger metal contents and may record stronger magnetic fields. So we're sort of thinking that lunar swirl source bodies are either some kind of magmatic feature or some kind of impact ejecta feature. The morphology of the Reiner gamma swirl, in particular, the main body, and this is a unique swirl, but it has this beautiful oval shape with these cusps. And so what's interesting about it is if you do forward modeling of magnetic fields, as done by Garrick, Bethel, and Kelly, you can form this type of shape by a magnetized elliptical disk and seeing what the field from that disk looks like at the surface, which is cool because it can explain the central anomaly at Reiner gamma, but it doesn't explain the fringes around it to the east and also to the southwest. But that's an interesting one. The idea that swirls could be magmatic or volcanic in origin is also interesting because Reiner gamma happens to be right next to the Marius Hills volcanic complex, which is one of the largest volcanic complexes on the moon. And so the question is, could these source bodies be dikes, lava tubes, sills, laccoliths? So that's a question that merits further exploration. And also there was this paper that came out this year by Hood and co-authors that suggested, based on connecting lines between magnetic anomalies and the Imbrium Basin, which is the largest basin on the near side of the moon, that perhaps all of these very strong anomalies are ejecta rays from the Imbrium impact, if you kind of connect the dots. So all in all, there's still a lot of uncertainty about what causes lunar swirls, but the good news is that we're going to make some headway this decade, hopefully, in terms of understanding how they formed. Because NASA just announced that there will be a commercial lunar payload service mission in 2024, and NASA selected Lunar Vertex as one of these CLIPS missions that will go to the moon. And this mission, Lunar Vertex, is going to go to Reiner gamma, that lunar swirl I just showed you, and it's going to measure incoming particle flux from the solar wind, and it's also going to measure magnetic fields. And so what we're going to learn is it's going to have a lander and a rover, and it's actually going to drive across one of the light-dark transitions and see how the field geometry changes. So I think we're gonna learn a lot about lunar swirls and lunar magnetism as a result of this mission, and I'm excited to be a small member of this mission, and I will have some involvement in that as well. Since I have another minute or a couple minutes in the talk, I'm just going to go ahead and show you this video, which NASA posted about this. Let me unmute it so you can hear it. Hi, this is Dave Blewett. I'm a planetary scientist at the Johns Hopkins University Applied Physics Lab. Lunar Vertex is a mission to an amazing place on the moon named Reiner gamma. It's the most famous example of a class of unusual bright markings called lunar swirls that spread across the surface of the moon in beautiful, complicated patterns. Strangely, the bright markings are found in areas where the rocks are magnetic. Lunar Vertex includes instruments on robotic landers to measure the strength of the magnetic field and the flow of charged particles from the sun. We also have a small rover that will drive as far as 500 meters from the lander, crossing from a bright swirl area into the dark background, while measuring the Lunar Vertex will help to solve the dual mysteries of the origin of the magnetic fields and the relationship with lunar swirls. All right.
That's great.
So hopefully you heard me, even if you didn't hear me.
Yeah, just a little bit broken, but I think we heard it. Yeah.
Yeah.
Well.
All right. So anyways, I'm really excited about the next few years because there's going to be a lot of really cool lunar magnetism research being done. So in conclusion, a combination of paleomagnetism and remnant crustal magnetism have demonstrated that the moon did generate a dynamo. The early dynamo, prior to about 3.5 billion years ago, at least at times rivaled the modern Earth's field in terms of its intensity. But it's possible that the average field during that high field epoch was weaker based on sort of those Apollo era results that need to be sort of reassessed. Dynamos driven by core convection and core crystallization can explain weaker magnetic fields less than a few microtesla, but the stronger fields may require non-traditional mantle evolution or non-traditional power sources like precession. And ongoing work, such as the Lunar Vertex mission, will elucidate the origin of crustal magnetic anomalies on the moon and will help determine if they are all impact related or exogenic, or whether they could be the result of endogenic magmatic products. And so with that, I will conclude, and I'm happy to take questions.
Yeah, thank you so much. It's a very, very, very systematic description. I was, I have like, okay. Anyone in the audience have questions to ask Sonia? Please unmute yourself and ask her the question. And if not, then I start asking you. I have a couple of questions to ask you, Sonia.
Sure.
Well, okay. About the everything, I think, kind of surround around this magnetic anomalies issue.
Mm-hmm.
The one of the how to say the standard model is to say that all those magnetic anomalies they are located. Most of them are at the antipodal locations, right? Even though you said that the more recent work have shown that the magnetization caused by the plasma cloud concentration of convergence is not enough to cause the magnetization. But then you still have the problem how to explain the antipodal correlation.
Yeah, so I think one thing that modeling paper did not cover, which is something that group is going to do next, is what happens if there is a dynamo field active at the time that impact occurs, basically. And so the idea is if you have an external field source and you have this plasma going around the moon, you have this magnetic reconnection effect that basically prevents strong magnetic fields from converging at the antipode and sort of shielding the lunar surface from those external fields. And so what happens if you actually have a dynamo field? Can you sort of trap the dynamo field by that plasma cloud and then get amplification at the antipode as a result of that? That remains to be seen. But I think that if you had a dynamo field around at the time, you might get the same kind of antipodal magnetization, but the field source is internal rather than external.
That the hypothesis in principle could be tested at the Mercury, because Mercury has a large, huge basin, impact basin called Coloris, and then if that's the case, we also see a magnetic anomaly on the antipodal side of Mercury.
Yeah, so the Messenger spacecraft did make some measurements of crustal magnetism at Mercury, and unfortunately, due to the orbit of the spacecraft, they could only make a crustal magnetic field map near the northern hemisphere. And so they actually found evidence for some strong crustal fields in the vicinity of the Coloris impact basin on Mercury, as well as a few other places. But I guess they weren't close enough to the Mercury surface on the opposite side from Coloris to actually conclude anything yet. But I think one of the great things that we could do is to actually make a really good magnetic map that includes the rest of Mercury and see if there is an antipodal magnetization there as well, like opposite Caloris. So yeah, definitely. There's certainly like that weird terrain at the Caloris antipode on Mercury. Like the surface geology is a little bit messed up in that region. So
Right.
yeah, I think that's a great place to look.
Yeah, maybe we should convince the BB Colombo, ESA BB Colombo mission to go very low, to the surface of Mercury to check the point. And you mentioned that the magnetism of the moon between the thermal generation and the we call it chemical generation, which is due to crystallization of the core. In between that period, it was said that might be maintained by precession. How big the precession has to be? Is the currently determined precession enough to keep that thing going?
Not currently, but in the past, it's possible that that effect was stronger. The idea is that whenever the Earth was closer to when the moon was closer to the Earth, let me put it that way, basically the effect of the Earth's gravitational pull on the lunar tidal bulge was stronger, and so you would have a more pronounced decoupling. Even this decoupling is still very small. It's like around 1 degree. But that's still enough according to this model. And you can read the paper, the first paper on this, which was by Dwyer et al. In 2011 in Nature, where they describe this. But even that seems to be, maybe enough to generate a field of tens of microtesla. There have not been, I would say, there have not been published magnetohydrodynamic models of this yet. That show that this works. But there is a postdoc working with Sabine Stanley at Johns Hopkins University, and that postdoc, Ankit Barrett, is doing models of a lunar precession dynamo, or at least a dynamo bolstered by precession, and is finding some promising results, at least from what I've seen at the conference abstracts. So that's something to look at. There's also been a more recent paper by Mathieu Dumberry and colleagues that looked at precession at the inner core, outer core boundary, and they can also generate fields of tens of microtesla potentially as a result of that boundary as well, kind of early in lunar history. So there's a lot more work that needs to be done on these non-traditional mechanisms, but I hope we can keep digging into them.
Oh, congratulations to your engagement with the what you call it, Lunar Vertex, right? Experiment.
Yeah.
And
very
it's all for you. And so because I was about to ask what would be the new things to do in that field, and you already said just let the mission. That's very good.
Yeah. I think we're potentially in an exciting time because there's that mission, and then hopefully NASA will actually send the Artemis missions to the moon, where we can have more samples returned by humans from the lunar South Pole. So assuming that works, I can do more like actual paleomagnetism too. So that would be great.
You mean going to the South Pole, or where you want to pick the lot? No, if you have if you can say, hey, I want to go to this place to pick the rock, and which place would you like to go?
Ooh, that's a good question.
I mean, like you want to go to.
I'm not sure that the South Pole, from a magnetism standpoint, I'm not sure that would be my first choice. Because a lot of
Rhino Gamma,
I would love to go to that area and get sample return. I would also like to go to the interior of South Pole Aitken Basin and get samples from there. That would be awesome. There's also some magnetic some of these antipodal anomalies happen to be, they're not just at the antipodes of the near side impact basins, they're also at the northwestern rim of South Pole Aitken Basin. And so there was another paper, which I didn't talk about in the talk, but in 2012, there was a paper that says that if you look at the shape of South Pole Aitken Basin, it's an ellipse, which means that it was a very oblique impact. And so if you had the impact in that direction, actually the ejecta from the core of the impactor would land in that spot. Yeah, and so there was this alternative hypothesis that maybe it's not antipodal magnetism, maybe it's the core of SPA that, kind of had its ejecta splosh down there and record magnetization. So I think that getting samples from that region would also be like very fascinating. So I wish we could get rocks from all over the moon. That would be great.
You have a chance.
Maybe that would be awesome.
The paper by Hood is Lonnie Hood, is it? 2021.
Yeah.
I have to read the paper. Yeah.
That is out in JGR Planets. So
that's a very interesting idea.
yeah.
And of course, he all has this idea of the antipodal, but with the ejector, focus on the other side.
Yeah.
So if he, according to his model, then you have the series of Lunar Vertex mission, to go to along the chain. Yeah.
Yeah, I wish we could just, it would be cool to have like a rover that just drove all over the moon and, measured everything everywhere. That would be so fun. But...
Okay. How about our colleagues in the audience? Do you have any questions? It's chance to ask. Because Sonia has been talking for an hour more. Okay, I think we learned a lot from your talk. I mean, it's great, and then and you have so much to do in next few years.
Yep. Well, thank you so much for the invitation. And if anyone has any more questions that they'd like to ask, feel free to email me, and I'm happy to correspond independently as well. But thank you so much. This was a lot of fun.
Yeah. Nishino-san, you have a question? We have another expert on this. Nishino, Dr. Nishino, he's involved in the Kaguya mission of JAXA.
Yeah. I just want to say thank you very much, Sonia.
Thank you.
It's a very interesting and impressive talk.
Thank you. It must have been very exciting to be involved with Kaguya. So
and Nishino-san, he wrote a number of very important papers on the solar wind interaction based on the meta-anomalies. So,
so actually, I'm curious about what's going on about inside the Rhino gamma magnetic anomalies. So, anyway, congratulations for acceptance of Vertex mission.
Yeah, thank you. I mean, I can't really take much credit for it because David Blewett is the PI, but I'm happy to be on the team, and I'll get to kind of play around with the data whenever we get it back. So, yep, it'll be great to learn more about what's actually causing the swirls. Yeah.
I think that in July, one of the coming talks will be given by Yoshifumi Saito. He will talk about the solar wind interaction with the meta-anomalies in particular. Yeah, it would be very interesting to hear that too.
Yeah, I mean, it would be great. If you want to send me an email, I'd be happy to tune in and listen to that.
Yeah, right.
So,
yeah. Okay, thank you so much.
Thank you, and you all have a great day. All right.
Yeah.
Bye.
Good night. Good night.